Hello, welcome at the third episode of a course in linear algebra. Today we're going to talk about vectors in the real space and manipulations as used in robotics, but also in gaming software and aircraft and car design. Episode 3. Vectors in real space. Have a look at this tensor. Does it have anything to do with the 3D space? Well, I don't think so. You can't say $3 to the north, €5 east and 80 elevation or something like that. It's just a tensor. Purely mathematically one could say okay, it's a domain, the currency space. But that has nothing to do with the real 3D space in which you can walk around. You're flying a helicopter. There's an infinite amount of directions you could fly into. Does this mean you're in a space with infinite dimensions? Well, actually not. That's not the way that dimensions are looked at. Let me explain. Suppose you'd find yourself in a point. You wouldn't be able to move anywhere. It's like a nail hit into a plank. There are 0 degrees of freedom. It's a 0-dimensional space. Things get better when you find yourself on a line. You have 1 degree of freedom, which is forward-backward, just like being in a narrow corridor. This is a 1-dimensional space. When you're on a plane, you can move back forward, but also turn left and right. So, a 2-dimensional space with 2 degrees of freedom. You could also move diagonally, but that's not an extra freedom. It's just a combined movement of the 2 freedoms that you already had. In the 3-dimensional space, you also have the freedom of going up and down. So, 3 degrees of freedom. A coordinate frame is nothing else than a reference in the 3D space. The origin of the frame is a point of reference as chosen by you, and the 3 axes point to a certain direction, also as chosen by you. You could orientate your frame, for instance, to the wind directions, like north and east, or according to the walls of a building, or any other orientation you choose. Suppose the origin is where you live, and the point is where you find yourself right now. You could move eastward, or you could move northward, or you could ascend in elevation, or you could move in combined directions. Now, in this part of the course, we will talk about tensors, of which the elements refer to the real 3D space. On the picture on the right, we could ask ourselves the question, what's the location of the tip of the candle? A better question would be, what path to travel to get from a chosen point of reference to the tip of the candle? To answer that question, we need units. We're talking about location or path, so we need length units. Centimeters, inches, yards. It doesn't matter what length units, as long as you use them in a consequent way. So, here are the units that I've chosen. And in my units, the location of the tip of the candle is 8, 5, 5. This is a first order tensor with 3 elements, because we live in a 3-dimensional world. Does it have to be 3? Well, no. If you work on a flat surface, then there is no z-axis, so there are only 2 elements. This type of tensors we'll call from now on vectors. We can have a vector in a 2-dimensional space or in a 3-dimensional space. So, what units do we use? Well, that depends. If you're talking about displacement from a certain point of reference, then we're talking about length units. Meters, yards, miles, etc. When we're talking about speed in a certain direction, then it's velocity units, for instance meters per second, miles per hour, etc. When we're talking about force in a certain direction, then it's force units, like newtons. It can be anything that has a magnitude and a direction in the real space. As a vector is only characterized by its magnitude and direction, we can shift it around anywhere we want. We don't change its properties as long as we don't change its direction or magnitude. The coordinates of the vector are always as seen from the vector's tail to its tip. The tail doesn't have to be in the direction of the frame. Think of wind. Suppose you're facing a southwest storm with wind power 12. Your partner, who's a few yards away from you, is facing exactly the same vector. Southwest storm with wind power 12. So one could more or less say that a vector is a drifter, as it doesn't possess an own location. It's true that a vector can define the location of an object relative to a reference point, but that's the location of the object. A vector itself doesn't have its own location. It only has the magnitude and the direction. When we come to think of it, we can define a vector in two ways. By its magnitude, as expressed in frame units and its direction relative to the frame, or by its projections onto the frame. But why are they called projections anyway? Well, if you shine light on the vector, then the shadow it throws on the axis is the projection. That's why they're called that way. Vectors are a special class of tensors, so the tensor rule of addition applies. This means that we can simply add the individual elements together to get the result. It's all nice and fine to say that the tensor rules apply, but is that true? Let's draw this in a frame. We calculated 14, 8, so let's draw it. Now let's shift the tail of the yellow vector to the head of the white one. It fits exactly, which makes sense, because no matter whether we travel over the white and yellow vectors, or we travel directly over the green vector, we end up at the same location. A guy walks from one side of the ship to the other side. It takes him a certain time to do so. In the same time, the ship moves 10 meters forward. The question is, what's the path that the guy traveled? There you go. When we choose our coordinate frame parallel with the path of the guy and the ship, then the displacement of the guy is 5, 0, and the displacement of the ship is 0, 10. We calculate the addition according to the tensor rules, and the result is 5, 10. That's the path that the guy traveled. We said it is allowed to shift the vector without changing its properties, so let's do so. And we see, no matter whether we travel over the dotted lines or over the continuous line, we will end up in the same position. We can also calculate the length of the path. There's a beautiful formula for that from the historic Mr. Pythagoras. I've done the calculation on the bottom of the page, and you see the result is 11.18 meters, the length of the path that the guy traveled. Vectors are a special class of tensors, so the tensor rules apply. We can apply addition in the same way we did with tensors, we can apply scaling in the same way, and the scalar product. Let's have a look at these two vectors. Both have the same direction, but they don't have the same magnitude. The second vector is twice as long. You see that both triangles have the same shape. Therefore, the proportions of the sides are the same. So, if we divide two sides of the small triangle, and we do the same with the big triangle, then the results will be the same. For instance, if we divide the 3 by the 5 on the small triangle, and we divide the 6 by the 10 on the big triangle, then both results will be the same. You can do so with any two sides of both triangles. The result will always be the same. Well, mathematicians in their wisdom have defined three divisions of sides. Y divided by r they call the sine. This is the opposite side of the angle divided by the length of the vector. X divided by r they call the cosine. that's the adjacent side divided by the length of the vector. And y divided by x is the tangent. All three divisions define the same angle alpha. Let's scale a vector with -1. We apply the vector rules by multiplying each element with -1, and when we look at the result, we see that the vector has turned into the opposite direction. So, multiplying a vector with -1 comes down to turning the vector into the opposite direction. Let's have a better look at what scaling actually does. We're going to talk about Euler angles, which is a very important subject. Euler angles determine the orientation of an object, such as an airplane or a robot. In order to understand Euler angles, we're going to look at the Euler rotation model. This mechanism can rotate the object by means of the red X ring, the green Y ring and the blue Z ring. If you rotate the object over X with the red X ring, then the other rings are not influenced, they stay in the same position. Therefore we call the X ring a child. This rotation is called roll. When we rotate with the green Y ring, then the red X ring moves along with it. Therefore we call the green ring a parent of the red ring. This rotation is called pitch. When we rotate with the blue Z ring, then both other rings move along with it. That's why we call the Z ring the main parent. This rotation is called yaw. Let's compare the human arm. The shoulder is the main parent of the arm. If you rotate over the shoulder joint, then the rest of the arm moves along with it. The wrist is a parent of the fingers. If you rotate with the wrist, then the fingers move along with it. So there we are, the Euler angles with roll, pitch and yaw. Is the blue Z ring always the main parent? Well, not necessarily. The blue Z ring is here the outer ring, but we could also have constructed another model where, for instance, the red X ring would have been the outer ring. In that case, the red ring would have been the main parent. An object in the 3D space can be defined by its orientation, which are the rotations against the reference frame XYZ with roll, pitch and yaw, and its location, which is the displacement against the reference point of that reference frame. Now we're going to talk about transformation. And here you see two examples where transformation is important. A robot that has to pick up an object that finds itself in a frame that's different from a robot's own frame. And an airplane that has an own frame that's different from the world frame. We're going to start very simple with a red frame in which you have a yellow vector. The length of the vector is 1. Therefore we call it a unit vector. Now let's rotate the vector over an angle phi. Then we have a look at the projection on the x-axis. Remember, projection means that we shine light on it and look at the projection that it throws. We had a definition of cosine, which was the adjacent side divided by the length of a vector, which is 1 in this case. So cosine is x divided by 1, which equals x. Therefore we can say x equals cosine phi. We can also have a look at the projection on the y-axis. In that case you have to divide the opposite side by the length of the vector, which is a sine. And at last but not least, we can have a look at the projection on the z-axis. The vector finds itself in the xy plane, so there is no projection on the z-axis. The projection on the z-axis is 0. We now put the projection results into a tensor. Now let's be a bit more ambitious and rotate an entire frame around the z-axis. The yellow frame consists of 3 unit vectors: x2, y2 and z2. We already saw the results of the projections of the yellow x2 onto the red frame. They were cosine phi, sine phi and 0. Now we're going to look at the projection of the y2 onto the red frame. The projection on the red x-axis is a sine. It's the opposite side divided by the length of the vector. However, x has a negative value here. We're dividing a negative x by the length of the vector, therefore a negative sign. The projection of y2 on the red y-axis is a cosine. It's the adjacent side divided by the length of the vector. And of course, the projection on the z-axis is again 0. In the third column, we're going to put the projections of the yellow z2 onto the red frame. Well, that's an easy one, because the yellow z2 doesn't have any projections on the xy, and its projection on the z is its own length. So 0, 0, 1. So there we are, the rotation matrix for turning an entire frame around the z-axis. Let's go ahead with a practical example. This battleship is sailing northeast, so it makes a 45-degree rotation against the z-axis of the red world frame that we have chosen according to the wind directions. The ship has a gun. The gun has an orientation within the yellow frame, which is the ship's own frame. This is shown by the green vector. Let's say the orientation is 1, minus 0.5, 0.4. The question is, what's the gun's orientation within the red world frame? In order to know that, we have to use the rotation matrix and make the scalar product with the green vector. I've worked it out. Here's the result. So far, we've only rotated around the z-axis. But of course, you can also rotate around the x or y-axis. Here are the 3 rotation matrices. Transformation is not only about rotation. There's also displacement. Displacing a frame is however much easier than rotating it. Let's displace the yellow frame over a path that we define as u, v, w. The frame simply displaces itself without rotation. So, displacement is just a question of addition with a vector. Let's get back to the example of the robot that has to pick up the green object, which the location is 8, 3, 1 as seen within the yellow frame. The robot, however, does not think in yellow coordinates. It has its own red robot frame. Let's say that the yellow frame is tilted by 45 degrees over the y-axis. That's a 45-degree rotation over y. Now, the first thing to do is to take the rotation matrix for y rotation and multiply it with the yellow position. Now, I've done the calculation and here is the result. But what does this actually mean? What this result means is the same rotation of the green vector, but then as seen within the red frame. Now, calculating the orientation of the green vector within the red frame is not enough. There's also displacement. You see that the origin of the red and yellow frames do not coincide. There is a displacement. Now let's say that displacement, as seen by the red frame, is minus 91, 5, 26. This we need to add with the result that we already had. And the result is then the location of the green object as seen through the eyes of the red frame. Let's repeat what we just saw. We wanted to transform a yellow work object position to the red robot frame. The yellow frame was rotated against the red frame, so we multiplied it with the Y rotation matrix. Then we added the displacement. We applied the calculation rules for tensors and came to this result. So what does this formula look like in general? Well, we have a certain position, let's say A, B, C, and multiply it with a rotation matrix. I'm not going to say rotation over X, Y or Z, just some general rotation matrix. We add displacement of D1, D2, D3 and apply the tensor rules. And there it is, the general formula. Now, mathematicians in their wisdom asked themselves the question, can we put both rotation and displacement into a single matrix? And they gave it a try. They added the displacement vector to the matrix. But then there was a problem, because you remember, to execute the scalar product, the length of the vector must equal the width of the matrix. So, this multiplication is not possible. But the mathematicians were clever and added something to it. They added 1 to each vector and 0, 0, 0, 1 to the matrix. But what's the meaning of those 1s? The 1 is not really part of the vector, because we live in a three-dimensional world, so the vector has only 3 elements. The 1 is only there to make this little trick work. Therefore, I'm going to call the 1 a dummy. It's not really part of the vector, but only there to make the calculation work. Now, I can imagine that you're puzzled. Why on earth would we want to do all this? Why do we want to jam both rotation and displacement into a single matrix? Well, there's a reason for that. Suppose we have an object in a yellow frame and we want to transfer it to the red frame. And from there to the purple frame. And from there to the pink frame. Having rotation and displacement in one single matrix means that we can simply multiply with each matrix. This makes life easier to make the calculations. Also for the software programmer, who can now write one routine and then he can apply that one routine again and again for each transformation. And here we're at the end of our course in linear algebra. Thank you for watching and don't forget to hit that well-known subscribe button below.